Hi, my name is Yunhao Xiao. Um, Today's presentation is about the integrating battery production and recycling through product lifecycle management for sustainable electric vehicle battery. My presentation will explore four key aspects of electric vehicle battery lifecycle management, including background, current challenges in electric vehicle battery lifecycle, the overview of product lifecycle management, and the integration of production and recycling of electric vehicle battery via the PLM. First of all, the left figure shows how widely lithium ion batteries are used and how their roles is evolving across the industries. Customers' electronics like the smartphone, the laptops are saturated market. Meanwhile, the transportation, including the electric cars and bus, is growing fast, and the growth energy along with renewable storage is booming. This really highlights how essential lithium ion batteries have become across various sectors. When it comes to battery types, there are three main designs, which are shown in the top right figure: the cylindrical cell, the pouch cell, and the prismatic cell. Let's take the cylindrical cells like the one Tesla used as an example. They are made up of three key components. Let me use the laser point. They are made with three functional components: the positive electrode, the negative electrode, and the separator. Interestingly, the positive electrode make up 27.5% of battery's weight and the negative electrode made 16%. Shows how vital those components are to the batteries overall. So in the realm of electric vehicle batteries, four dominant positive electrode material are commonly used, are shown in the left figure. Among those, the NCA, the nickel, cobalt, and aluminum material, which contains lithium, nickel, cobalt, and aluminum, powered the Tesla vehicle, the Model 3, the most popular electric vehicle in the United States, and the first EV from the luxurious brand Rolls-Royce, the Spectre, featured with a 102 kilowatts hour NCM battery pack, which replaced the replaced the aluminum with the magnets for enhanced performance. Um, the the Nissan Leaf used the lithium titanium oxide mixed with the nickel with the NCM at its batteries. Meanwhile, the Xiaomi SU7, often regarded as the most beautiful sedans from China, offers the cost-effective alternative by using the lithium iron phosphate (LFP) in its basic models. The the periodic table shown on the right highlights the feasible and economically visible elements used for battery electrode material. For positive electrode, elements such as the lithium, sodium, cobalt, the nickel, the manganese, and aluminum sulfide, phosphate are in high demand for industrial battery manufacturing, reflecting their importance in advancing electric vehicle technology. So, the global lithium ion battery market is experiencing rapid expansion, with projects indicating growing from the 15.156.8 billion in 2023 to 187.1 billion by 2032. Simultaneously, a report from the RMIS of the European Commission highlights that the global demand for raw materials such as nickel, graphite, and lithium is expected to increase by 2019 and 14 times respectively by 2040s compared with 2020. This surging demand of the uh, this surging demand of the material create the pressure of crucial lithium ion electrode, emphasizing the urgent need for sustainable resources management and innovative recycling solutions. So this figure illustrates how PLM manages the electrode vehicle's life cycles from inception to the disposal, including six key components: the concept, development, the validate, the product, the produce, the in use, and second life. For electric vehicle backpack, integrating the production with the recycling through the PLM provides a smarter approach to addressing crucial challenges such as material shortage and waste management. In this presentation, I will dive deeper into three selected steps which marked here um, of the PLM process, which is the cell manufacturing, the product monitoring and maintenance, the battery cascade utilization and recycling, to explore those their impact on electric vehicle battery life cycling management. So first of all, to further illustrate the integration of production and recycling with PLM, we can examine the cell manufacturing process in detail first, where the digital twin, which is showing the red figure here, the digital twin framework and the advanced technologies like machine learning plays a crucial role in optimizing the key steps such as electrode preparation, here the mixing, coating, the cylindering stuffs, and the um, cell assembly and the activation. Those three layers structure of digital twin for large scale lithium ion battery production, outlining the key steps: the electrode preparation, the cell assembly, and the activation by formation steps. During the electrode fabrication, the active materials such as the carbon and the binder are incorporated to enhance the conductivity of the active material. The proportion and quality of the mixing play a crucial role in determining the weight and the energy density of the battery pack. To optimize the utilization of active material, machine learning is implied from here to optimize the utilization of active material and the processing conditions and also predict how manufacturing parameters influence the electrode mixing and the performance. Instead of just focusing on optimizing powder mixing, machine learning is now applied across every aspect of the battery manufacturing. This includes the slurry making, um, the electrode coating, the drying, and even the analyzing the electrochemical performance of the um, as assembled battery, which is shown in the top left figure. The bottom left figure gives a great example of how machine learning can improve coding uniformity by using the predictive model. Here you can machine learning helps evaluate how factors like the amount of solid electrolyte, the liquid to solid ratio, and the solvent composition affect the uniformity of thin film electrolyte. This ensures a more consistent and a higher performance battery, which is a big steps toward the manufacturing. Once the battery is installed to the vehicle, which is shown in the left figure, The PLM focus on monitoring and maintaining its performance, while the battery management system, the BMS, being a premium example, which the function of the BMS is shown in the red figure. The BMS is like the brain of the battery pack, working to ensure it operates safely, efficiently, and lasts as long as possible. The red figure shows some of the key functions of the BMS, like it's monitoring the important parameters like the voltage, current, temperature, and state of charge, the SOC of each cell and the entire battery pack, and also balancing every parts the all cells to prevent the imbalances that could damage the battery, and also manage the temperature, keeping the battery from overheating and freezing, which can affect the performance and lifetime, and also provide the protection, self protection, and estimation um, to track the battery state of health, predicting how much life is left, and when maintenance or replacements might be needed. And also, it commutes with the real-time data with system like the vehicle control unit, and to detect the any default, helping with maintenance and troubleshooting before problem emerged. Also, uh, by performing of those tasks, the BMS plays a huge role in extending the battery's life, improving the safety, and ensuring your EV running efficiently. However, after 3 to 5 years of use, when your EV range starts to fall below your expectation, it's usually the time to replace the battery. So the electric vehicle battery are typically retired when their capacity drops to around 70 to 80%. Well, it might not work well for the vehicles anymore, but those batteries can still be put to good use elsewhere. The figure here shows the cascade utilization, where the used electric vehicle battery are repurposed for secondary application. This gives them the secondary life, whether used for the energy storage system, the power housing, or even like small devices or small like vehicles. This is a smart way to get the most value out of those batteries and reduce waste and promoting the sustainability. So the key steps for the material for the battery cascade utilization contains 4 steps. The first is battery assessment to remove the battery from the decomposition to from the EV battery pack, and the reconfiguration to make sure it can be fit in the any applications they're gonna be used for its second life. And also the second battery, they list the secondary battery applications here, and eventually when those repurposed batteries eventually reaches to the end of their life, they are recycled to recover valuable materials like lithium, cobalt, and nickel. Those materials are then used to make new battery, creating a full circle of sustainability. So here, when electric vehicle battery reach their end of life, they undergo steps like discharge, disassembly before the cycling through three main method. They direct the recycling, the parallel, and the hydro recycling process. So first of all, they direct recycling recover active materials like NCM powder through the lithium additions and the calcination, and it's minimized the waste and allows the material to be reused directly in the new material. And for the parallel method, they use the high temperature to um, recover the material like cobalt or nickel or the aluminum, the lithium, and well, but it produced the emission, so requiring more treatment for the environment. And finally, for the hydro method involving the electrode processes like acid leaching or precipitation to recover the lithium, or the transition method like cobalt or other materials, offering the high recovery rates with great sustainability. And in the right hand side, there are three icons from the company. The top three companies, recycling companies in the United States. The first is the Redwood, combine the hydro and pyro process to recover over 95% of material like the nickel, cobalt, and lithium. And also, it has a deep relationship with the Tesla, so which is the material vendor for the um, Tesla. And also, it's the lithium cycle used shredded the battery into the black mass for centralized processing and the material extraction. And the ABCT, which is the American Battery Technology Company, which also employs a closed loop process to recover high purity material, meeting the new material standards. So those methods and companies demonstrates how recycling supports the circular economy, reduce wastes, and ensure efficient resources using in the electric vehicle battery life cycle. And here comes to a very vivid example. The left figure highlights the collaboration between the Jaguar Land Rover and a British recycling companies, which launched a pioneering project to manufacture the test EV battery cells use the recycled material from the old Jaguar electric vehicles. And here shows the similar flow chart. They used the hydro method to first get the black mask, and by using the acid leaching process to separate the graphite and recover the valuable metals. And after this, during due through the high temperature synthesize to regenerate the NCM or the other type of active cathode material, and reuse those material for the new battery manufacturing. This innovative align with the product life management by promoting sustainability, extending the life cycle of valuable resources. So finally, to summarize, the product life management bring everything to this circle in electric vehicle management. It's a focus in design battery that can be recycled, optimizing how they are used, and reuse recover material to make new ones. So this approach keeps things sustainable, reduces waste, and ensures we make the most of our resources. So thank you very much for listening.